Hi, my name is Mahavir Singh and I am going to discuss the RVE and its use to predict the mechanical behavior of fiber matrix composite. In this short video I will touch on what is RVE and how it look in context of fiber composites and the parameters which affect the RVE, and then in the end there will be three finite element simulations for different sets of loading to calculate the mechanical properties of fiber composites. So RVE, as the name suggests it all, the element means it's a part of bigger geometry, and volume says that we are talking in geometrical space sense, and representative says that it's the criteria to select some geometry as representative volume element or RVE. So this is mainly discussed for heterogeneous material, because in homogeneous material the properties are same everywhere, so any size of any volume element can be called as RVE. So if we see the fiber composite like this, so we can select any volume like this or like this. So suppose this we have selected as our volume element. Can we call this as a representative volume element? Yes, we can call, and it can represent the properties of the entire matrix. We can also select the material, the volume like this, which has hexagonal symmetry, and even smaller volume element should do the job. We can change the geometry like this, which will also represent the material behavior. Similarly, these geometry will also represent the material behavior, but they will not be repetitive. They cannot be placed against each other to make the whole fiber composite. And if we further reduce the size like this, then there could be dominance of the matrix properties or the fiber properties. So by this we can say that the representative volume element is affected by size, its shape, the location where it is chosen, and the symmetry, and the boundary condition which is being applied over it to compute the mechanical properties. So in short, it's a small volume, small possible volume, which should represent the entire material behavior. And why we want to select this as a small volume? Because we want to make our calculations easy. So the material properties are obtained by using the strain energy principle, and this strain energy stored in the material when equated to work done on it, it can give stress if the strain is known, or strain if stress is known. And strain energy for any general material can be written as a product of stress and strain and integrated over the entire volume. And generally for homogeneous material it is written as average stress and average strain in the material, and when multiplied with the total volume it gives the total strain energy. But this expression of strain energy is also applicable for heterogeneous material as well. I am going to make a short separate video for this where I'll prove that u prime is equal to u. For this time, let's take it as a fact that I can use this expression to compute the strain energy, where sigma bar ij is the summation of sigma ij at each and every point and divided by volume, and similarly sigma ij is average strain component. So now we want to calculate strain by using the divergence theorem. So if we see on the right side, so Eij is expressed as 1 by V over integration of epsilon ij dV, and this epsilon ij can be written from strain displacement relationship as Ui differentiated over xj and Uj differentiated over xi. So I can take 1 by 2 out, and when I apply the Gauss divergence theorem, it it will become, the volume integral become surface integral, and the curl of ui by curl of xj will be converted to the normal vector nj, and the dv will be small volume ds. So advantage of using this is that if I know u at surface, then I can compute eij, average eij, very easily. So if we take the example of a fiber matrix composite here, matrix as a whole, I can treat this as a continuous material, and I can use Gauss divergence theorem. Similarly, fiber, I can treat this as a continuous material, and I can use the Gauss divergence theorem. For fiber, I can simply write as a anticlockwise integration over this surface area S1. For matrix, I can write for S2 as this closed curve. This will be cancelled out, and negative of this one for S1 curve as this one. And when these are combined together, and if they are perfectly bonded, this S1 integral and this S1 integral will be cancelled out, because u will be same. ui means u, v, w, all three component will be same at this boundary, and for that purpose we can compute eij by simply computing the ui and uj at this outer surface of the RVE considered. So there are three models used in this particular analysis as normal loading and two types of shear loading. So for normal loading, they have taken this quarter part of the entire RVE, and because of symmetry, this face will not move in y direction and this face will not move in z direction, and u on this face will be delta 1. Whether u on this face, the backside face, will be 0. Similarly, v on this backside face is 0, and v on this face will be delta 2, and w on this face will be delta 3, and w on the downside face will be 0. So these are the boundary conditions dictated here, and I can compute epsilon I1 when I have applied a load P on this face, so I can compute epsilon 1 by Gauss divergence theorem by the multiplication of, by knowing the u1 on this face, which is delta 1, and this will give me epsilon 1 as simply delta 1 by A. So once I know this, I can use my total strain energy with the simple expression of average quantity, and I can write W as 1 by 2, load applied is P, and the deflection at the point of application of load is delta 1, and when these two are equated, they gives as sigma 1 equal to PL by BC. So once I know sigma 1, once I know epsilon 1, I can compute E1 as ratio of sigma 1 by epsilon 1. I can also compute mu 12 equal to negative of strain in two direction divided by normal strain in one direction. This will be minus delta 2A by delta 1B. So this is it for normal loading, and for transverse shear loading, the stress field and strain field in these direction, y and g direction, has no dependence on x direction. So for that purpose, only plane strain 2D geometry has been considered to analyze this one, and in this case, in the earlier study, it was assumed that this will deform like a complete parallelogram, so that this face will always remain plane. In this particular analysis, this condition is not being imposed, and to know that what will be the displacement over these boundaries, it has been considered to be a bigger space of 9 fibers, and by applying the the shear stress on the boundary of this one, the displacement around this RVE is measured, and those displacement are imposed in this model as the input to specify boundary conditions. So it was noticed in this experiment that V on plus and minus B phase are equal. In this phase the V is equal to this phase. Similarly, W on this phase is equal to this W at this phase. So whatever be the displacement here will be same as here. They may have some distortion, that they may have V and W varying along this length, but at this point and this point they are same. Similarly, on this Z phase, V and W are same as on this Z is equal to minus C. And also we know that epsilon ZZ, which is normal strain on this phase and this phase, is 0. So whatever be the displacement here will be same at this point. And epsilon YY is also 0. So whatever be the displacement at this point will be same as displacement at this point. So this is delta Y, delta 2, and in this Z direction it is delta 1. Now we have fixed this point with the roller support, making delta 1 as equal to 0, and we are left with only delta 2, which is in Y direction. And strain can be computed by integration of this delta 2 3 point wise, and we know from Gauss divergence theorem we have to 1 by V will be 1 by 4 BC. The x direction is taken as unit, and this one integrated in a closed boundary like this, this will turns out to be delta B, delta B, delta B, delta B. This will be 4 delta B. So gamma 2 3 is equal to delta 2 by C, and we can use the work done applied on this point equal to 4 into 1 by 2 of B into delta. So this will be total work done, and which when equated to total strain energy stored in the material, this will give us the stress 2 3 component equal to P by B. So once we know gamma 2 3, once we know sigma 2 3, we can compute G 2 3 as PC by B delta 2. Similarly, for longitudinal shear, we are applying the shear on this face. Y is equal to 2B, and we are fixing this as a constraint. So in the constraint we have U, V and W on this face as 0. Also U on this face is equal to delta, and there is no movement allowed in Y direction on this face. It can move in this direction, but it cannot go like this. And the boundary conditions are U, V and W on this face are same as U, V and W on this face. So by knowing these boundary conditions, we can compute delta 1 2 from Gauss divergence theorem, and I have written simply as it will be delta by 2B. Delta by 2B. This is the shear strain in this element. This will be constant over the entire phase. And from work done, we can compute work done as 1 by 2 P into delta, and when these are equated together, the strain energy and work done, they gives sigma 1 2 as P by 2 AC. So we can compute G12 as the ratio of sigma 1 2 by gamma 1 2, which will be PB by AC delta. So we know G12, we know G23, we know E1, E2, mu12, mu23. So that should give us all the properties. So this is the result from the experiment and from these particular simulations, and also some of the references are taken to know the agreement or disagreement. So this shows that the first one, E11, has a great agreement with experiment, also with the reference. The only disagreement is mu12, which is giving very low value. Also it gives low value in the references in the earlier simulations, but in experiment it gives little bit higher value. Here also this is comparable in this AS435016 composite. This is comparable. So thank you very much.